In section 6.3, we're going to look at finding trigonometric functions of any angle. And so that's going to allow us to position our triangles outside of quadrant 1, where we've primarily been working where everything is positive. So if we consider an angle that is an obtuse angle, such as this angle right here, we would note that it would be referenced by a triangle in quadrant 2, or we could have it in quadrant 3 or 4, where some of our coordinates are going to be negative. Just a quick teaser at what we're looking at. So in order to be able to do this, we're going to need to find angles that are coterminal with a given angle. That's going to work in with finding complements and supplements of those given angles as well. Then we're going to be finding our 6 trigonometric function values for any angle in standard position, where the coordinate points of the terminal side of that angle are given. We're going to find the function values for any angle whose terminal side lies on an axis. And then we'll also continue and study the function values for an angle whose terminal side makes the special angles of 30, 45, and 60 with the x-axis. And then last, calculator to find function values and angles when those are not the special angles of 30, 45, and 60. All right, so a teaser of what's coming up in this section. Let's go ahead and look at topic 1. We're working on angles, rotations, and degree measure. So definitions and vocabulary here. For our words angle and initial and terminal, looking across here, we've got our angle as defined between 2 arcs. So whatever our first arc is and our second arc here, arc is the actual angle, rays. The first ray and the second ray, the angle is the measurement of the arc in between those. So just a diagram of an angle. And we can have angles that are acute, less than 90 degrees. And we can also have angles that are obtuse, that are more than 90 degrees. And we'll be able to work with all types of angles coming up in this section. All right, on to the initial and terminal side right here. And I'm going to relate that to standard position. So when I look at standard position, in standard position, when we consider our x and y axes, if we draw an angle, so we draw one here in pink, if I draw an angle, that angle is assumed to be measured from the positive x-axis side. So if I use another color and draw another angle down here, that angle is again assumed to be measured from the positive x-axis. So it's not always the shortest angle. We can talk about measuring in the positive rotation and the negative rotation, which we'll talk about in just a second. But standard position, we're going to be measuring from the positive x-axis, and our angles are measured counterclockwise. So with that, in our initial and terminal position, the initial position is typically going to be defined here as the x-axis, and then the terminal side, wherever that is going to be the ending of the arc that we measure. So often we'll draw a little arrow to show the rotation of that arc for that angle right there, although sometimes we'll just draw like the single angular measurement as seen over here. So the arc is not necessary unless you're not drawing in the standard orientation. Okay, and then quadrant, of course. So we need to talk about our quadrants. Again, in terms of the XY axes, we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So we will be referring to our angles as having a terminal side in quadrant 1, 2, 3, or 4. This angle, as an example, has a terminal side in quadrant 2, terminal side in quadrant 1, and that one down there is a terminal in quadrant 3. Okay, so a little bit of review and some perhaps new terms right here, defining our way we're going to be phrasing our angles. All right, some additional diagrams here to go along with it. So we've got ourselves an angle here in standard position. We can see the initial side on the positive x-axis. And we can see the terminal side, it looks like in quadrant 1 in this case right here, and our angle being the measure between those in the positive orientation. As you can see, the arrow is drawn to show positive rotation. And then the vertex is just going to be typically at 0, 0. If this is in standard position, that vertex is going to be at the origin right there, as we can see that it is. Okay. Another example right here, we've got our initial side right here on the positive x-axis. Our terminal side, in this case, is in quadrant 2. And once again, this is demonstrating what a positive rotation looks like for an angle. Positive rotation being a counterclockwise rotation. And then in the final diagram over here, initial side always on the positive x-axis. Terminal side on this angle does appear to be in quadrant 3 this time. Now, the positive rotation on this angle would be outside this arc right here. That would be a positive rotation measure for this angle, but we can also consider the negative orientation for this angle if we wanted to look in the reverse direction. Okay, so every terminal side has both a positive and negative rotation. This one right here would have a negative rotation back over in this direction. So there are going to be multiple ways to express the same angle. We can talk about the positive rotation or the negative rotation. And I'm going to label the other one over here. Again, the one I drew in the yellow highlighter over here would have been the positive rotation for this angle. Positive rotation counterclockwise, negative rotation or negative angle will be in the clockwise direction. Okay. Bottom of the page here, example 1, find one positive and one negative angle that is coterminal with each of the following and then state which quadrant they are in. All right, so I'm actually going to state my quadrant on this one first. I like to draw a diagram as we're doing this. So my diagram right here for 74 degrees, starting on the x-axis right here, if I went all the way up to the y-axis, that would be 90 degrees. And so I know that 74 degrees is going to be somewhere short of 90 degrees. And it's more than halfway there, so that's what I'm attempting to draw in this picture right here. That is a 74 degree, approximately 74 degree angle. Now, my goal in this question is to write one positive angle and one negative angle that is coterminal with each of the following. So coterminal means that they're going to share a terminal side, same terminal side. Coterminal here means that they're going to have the same terminal side. So the negative one, if we do that one first, we would say that instead of rotating up to this angle, I would rotate down and back around to this angle. So one of the things that I'm going to need to know here is how many degrees would be in a full rotation. But if I consider that there are 90 degrees in each of the quadrants, 90 degrees all the way around, 90 plus 90 is 180 degrees. Plus 90, that's 270, plus 90 is 360. So a full circle angle is going to be 360 degrees. Okay, so if I'm going to go backwards, I'm going to be just shy of a full rotation by 74 degrees. So my negative angle is going to be 74 degrees minus 360 degrees. So if I subtract 74 minus 360, that's going to come out as an angle measurement of negative 286 degrees. So that's going to be a negative angle that has the exact same coterminal side. That angle measured backwards of negative 284 degrees would end in the same place. Now, if I wanted to have a positive angle that was going to land in the same place, 74 is the shortest positive angle, but I also could measure up to this angle, and then go all the way around and back and land on it again. So I can spin around multiple times to end on that same place. In that case, I've made one full circle, 360 degrees, plus the additional 74 degrees. So I'm going to take 74 degrees plus 360 degrees, and that's going to end us at 434 degrees. So these angles are identical ways of saying 74 degrees. 74 degrees is in this case, the simplest possible positive angle, but I also can talk about the negative angle and multiple rotations. I could have more of these if I subtracted another 360 or added another 360 and moved around again and again and again. So there's no limit to the number of angles that are going to have the same coterminal side. They'll just be larger and larger than the ones previously listed. All right, so let's take that idea on to the next one. This angle here, let's see, I was supposed to state what quadrant this was in. Let me just go back and say these are in quadrant 1, all of them. Let's go back over on this one, make ourselves a little diagram. This is already negative, and negative 90 would be all the way down to the negative y-axis. So at negative 81, I'm not quite there. This is going to be the angle at negative 81.3. Again, just approximating that it's not quite to negative 90, almost all the way there at negative 81. And so this is going to be an angle that's in quadrant 4. So the simplest possible way to state this is the negative 81.3 degrees in negative orientation. However, if we wanted to talk about this one in positive orientation, we would need to go around the circle in the other direction, and that's going to end us just shy of 360 by the measure of negative 81.3. So I take negative 81.3 and I add 360 to it. That would make the angle in the positive rotation 278.7 degrees. Now, my goal is to list one positive and one negative angle. So another negative angle would be I would need to go backwards more than once. So I need to take my negative 81.3 and subtract a 360 to go in the reverse direction by another 360 degrees. That would end up at so we take negative 81.3 minus 360, a negative 441.3. And again, those are both the same as the negative 81.3 degrees. So 3 ways to express that same angle. One of them has a positive angle, and then there are 2 that have negative since the original was expressed with a negative angle. All right. Recall from one of the previous sections that the definition of complementary, 2 angles are going to be complementary if those angles add up to 90 degrees. And 2 angles are called supplementary if those angles add up to 180 degrees. So we'll talk about those words, just wanted to refresh those as they come up in the next couple of topics here. Okay, so my next topic, we're going to find the trigonometric functions of angles or rotations. Up to this point, we've defined the 6 trigonometric functions in terms of acute angles, but like many things, we can take that concept and generalize it to any angle or rotation. What matters is where the rotation ends. Okay. So we're going to be constructing reference triangles based on any standard angle, and then we're going to redefine the 6 trigonometric functions. For an angle that is in quadrant 1, the reference triangle, is the same thing as the original triangles that we were constructing our trigonometric ratios off of. We've got ourselves a triangle here where the angle is inside of the triangle in standard notation. If our angle is not in the first quadrant, like this example over here that's in the second quadrant, we can see that we have a reference triangle that is actually outside of the angle right here. We are able to use this angle to compute the trigonometric ratios for this one. For things that have a reference angle that is one of our special angles, we'll be able to figure out the trigonometric functions for the bigger angle in relation to the trigonometric ratios for the reference angle. If that reference angle down here is a 30, 60, or a 45 degree, then the trigonometric ratios for the bigger angle will be either positive or negative of those same values for the trig ratios of the 30, 45, and 60. So we'll talk about that as we get to the positive and negative section on the bottom of the page. Another key point right here in these diagrams is we have been talking about our angle and our triangle in terms of the side opposite, the side adjacent, and the side hypotenuse. This has been reformatted right here to think about these in terms of the ordered pair, where I end the arc right here, and we're just ending the arc on some circle. So I've got this ordered pair, again, as the x coordinate and the y coordinate, and we're going to use the y coordinate as the side that is opposite. And that's true in both of these, right? The y coordinate for my angle is the side opposite of my angle or its reference angle. And the x coordinate is the side adjacent. The x coordinate is the side adjacent to the angle. And then the hypotenuse right here, we're calling this r, and we're calling r just to stand for the radius of this circle that we would imagine spinning if this angle was allowed to spin into any quadrant. We just use r for radius in terms of the hypotenuse. So the Pythagorean theorem becomes x squared plus y squared equals r squared instead of a squared, b squared, c squared if we're using the labels x, y, and r for the sides of the triangle. Okay, so with this in mind, the sine of the angle, we know the sine is always equal to the opposite divided by the hypotenuse. The opposite side is y divided by the hypotenuse side is r. So my sine function is now equal to the y value divided by the r value. The cosine would be equal to the x coordinate divided by the r value, adjacent divided by hypotenuse. So that's going to be x divided by r for cosine. The tangent is equal to the opposite divided by the adjacent. So that's going to be the y value divided by the x value. And once we have our primary three functions, we can take their reciprocals to get the reciprocal three functions. So the sine function is going to be the reciprocal of the cosecant function. If sine is y over r, then cosecant is going to be r over y. We know that if cosine is x over r, secant is going to be r over x. And we know that if the tangent function is y over x, then the cotangent function is going to be x over y. All right, now note that based on the quadrant, the x values can be positive or negative. The y values can be positive or negative, but the r value is always positive. So this is an important thing for us to keep in mind as we are working on our ratios right here. R is always positive, and that's because it is a distance measurement. It is a radius of a circle. R is always a positive value. X and y, though, could be positive or negative. So we're going to make a note of this here. X and y can be positive or negative. And this diagram at the bottom just illustrates when each of those are positive or negative. So I know in quadrant 1, the x value is positive, and in quadrant 4, the x value is positive. X is positive on the two that are on the right-hand side. I know that x is negative on the two that are on the left-hand side. And then for y, I know that y is positive on the two that are in the top. And I know that y is negative for the two that are in the bottom. That's where the y coordinates are going to be negative, right? Positive x coordinate, positive y coordinate, negative x coordinate, negative y coordinate. So our coordinates are positive, positive, negative, positive, negative, negative, and positive, negative, respectively. Okay, now as a result, if we're thinking about the sign, positive or negative, of the sine, cosine, and tangent functions, just the primary three, because we know that sine deals with y and r, sine is going to be positive where y is positive. So y is positive in both top coordinates. So sine is positive in quadrant 2, and it's also positive in quadrant 1. They're actually all positive in quadrant 1. If I think about cosine, cosine deals with x over r. Remember, r is always positive. So cosine is positive where x is positive. So cosine is going to be positive in the first and fourth quadrants here. And then tangent. Tangent is x divided by y. So when they're both positive, tangent is going to be positive. Where you have one of each, when you divide those, you'll get a negative. But where you have two negatives, when you divide those, you will get a positive. So tangent is going to be positive, where you have either both x and y positive or both x and y negative. Okay. And then we talked about the positive ones, so of course the negative ones follow from reverse there. All right. Okay, so my next goal is to find the 6 trigonometric function values for the following angle. In order to find the trigonometric values, I need to know the 3 sides of this triangle. So the coordinates here are negative 12, which means the x coordinate is negative 12. So that's the distance across the bottom. And the y coordinate is 5. So the y coordinate is the height over here. So this is 5. I can find the hypotenuse using the Pythagorean theorem. So find r. So we'll take 5 squared plus negative 12 squared equals r squared. So that's 25 plus 144. That adds up to 169. And if I take the square root of both sides, we're going to end up with 13. It is plus or minus the square root of 169. So it is plus or minus 13. But because we know that r is always positive, we are going to select the positive. So r is 13. X and y, whether you select positive or negative, is going to depend on the quadrant. So in quadrant 2, the y coordinates are supposed to be positive, as you can see, and the x coordinates are supposed to be negative, as you can see. So these two signs have been selected appropriately for an angle in quadrant 2. All right, now that we know the value of r, which is 13, we're going to find the 6 trigonometric functions for the angle beta. Notice that the angle beta spun around twice to lie coterminal to this side, but it doesn't matter if I'm looking at a big angle or I'm looking at the smaller angle or even the angle inside, they all have the same trigonometric ratios because they all have the same coterminal side. So let's find the sine of angle beta. From this angle, I'm looking at this corner of the triangle, so opposite over hypotenuse, that's going to be 5 over 13. That's our y coordinate divided by our radius. We're going to need the cosine of beta. So adjacent over hypotenuse, that's going to be our negative 12 over our 13, or our x coordinate over our r value. We want the tangent of beta. That's going to be opposite over adjacent. So it's going to be 5 over negative 12, which simplifies to negative 5/12. Just can't leave a negative in the denominator. It can be out front or on top. And again, that is the y-coordinate divided by the x-coordinate. Those are the primary three, so we'll get the others as well. The cosecant of beta, reciprocal of sine, that's going to be 13/5. The secant of beta, reciprocal of cosine, that's going to be negative 13/12. So I just went ahead and left the negative because it needs to stay on top. And then the cotangent of beta is going to be negative 12/5. Okay, so we know the 6 trigonometric ratios for the angle beta there. So point at the middle of the page here. The value of a trigonometric function depends only on the angle, not on the choice of point on the coterminal side, because the angle remains the same at any distance. So that is to say, if I had made this, instead of the ordered pair negative 12/5, if I had found this ordered pair and made my triangle here and had smaller values, maybe had negative 6, 2.5, just a different ordered pair that would fall on that same line, they would have gotten the same exact ratios. Okay. And we saw that in an earlier section as well, so we're just kind of expanding on that idea. In example 3, we are given a description and told that the terminal side of an angle in standard position lies on this line in quadrant 2. And we want to find the exact values of the 6 trigonometric functions for this angle. So let's see if we can make a diagram for this line. I'm going to solve for y so that it helps me graph it. Y would be equal to negative 4x. Okay. And I'm going to make myself a graph. I know that this line has a slope of negative 4, and it has a y-intercept at 0, 0, since there is no b value. It was 0. So I'm going to have a point at the origin, which I need actually to create an angle that's going to have a vertex at the origin. So that's good. And the slope is negative 4. So we're going to go down 4 over 1. Or we could go up 4, back 1. All right. So I'm going to grab a ruler real quick and make a quick sketch of this line. So this line does cross through quadrants 2 and quadrant 4, but we are told that the angle is going to have terminal side in quadrant 2, so that lets me see that I'm looking at an angle with position like this. Now I do have an ordered pair right here of negative 1, 4, and I can drop that down and look at this little triangle right here. So I'm going to make that little triangle that I just drew a little bigger. This is the triangle that we're looking at. It had 4 as its y-coordinate, its height, and negative 1 as its x-coordinate. The ordered pair at the top was negative 1, 4. Okay. So my angle, oops, there we go, is outside there, corresponds to the same thing as this reference angle on the inside. So when I find the 6 trigonometric function values, I'm going to be using these values here for opposite and adjacent. I still do need to find the hypotenuse, so we are going to use the Pythagorean theorem there. Negative 1 squared plus 4 squared equals r squared, or c, whatever you want to call it. So that's going to be 1 plus 16 equals r squared. So that's 17 for r squared. And we end up with square root of 17 for r. We know that the hypotenuse value is always positive, And I've already selected the sign, positive or negative, based on the fact that I'm in quadrant 2, where the x coordinates are negative and the y coordinates are positive. Okay, so let's find the 6 trigonometric ratios. I haven't named this angle, so let me go ahead and name this angle theta. And let's find the sine of theta. Sine of theta is going to be opposite, which is the y value of 4, over the hypotenuse, which is the square root of 17. There's no need to rationalize these unless you have a special angle, which we don't. This isn't one of our special angles, like square root of 2 over 2 is the ratio, so we're not going to bother rationalizing. So cosine of theta, I don't know why I do a beta, I was thinking up there. Cosine of theta, same angle. X value, -1 over the square root of 17. And tangent of theta is the opposite over the adjacent. So that's going to be y over x. That's 4 over -1 or -4. Those are the primary three. So now let's get the reciprocals. Cosecant of theta is the square root of 17 over 4. I accidentally wrote a 14. It's supposed to be a 17. Just trying to flip this over. Gotta watch my writing here. Secant of theta, let's flip this over. So that's going to be the square root of 17 over -1, or negative the square root of 17. And then cotangent of theta, which is going to be -1 over 4. All right. Now, these answers are absolutely fine on paper right here. We've got our 6 function values for this angle. Not rationalized. So I don't have to rationalize these by hand. I would leave these as is for my sine, cosine, tan, cosecant, secant, and cotan. However, if you are doing homework in my math lab, you may have to rationalize. So just wanted to show one of these. If I do need to rationalize for some other reason, not necessarily for your teacher, but for my math lab, you would do so, and you might have to write this as 4 times the square root of 17 over 17, and that would be the rationalized version of this. It's not difficult to rationalize. You just multiply by the square root top and bottom, but it's not something that you have to do by hand. Don't waste the time. If you're doing it on my math lab, just one little extra step to make sure you can enter your answers correctly. Okay. Example 4. A function's value and quadrants are given. Find the values of the other 5 trigonometric functions. Okay. So sine of alpha is equal to -1/3, and it's in quadrant 3. So if I've got an angle in quadrant 3, it's going to be down here somewhere. So my angle is going to look like this, and the reference triangle would be drawn from that angle up into the closest version of the x-axis. The reference angle always connects to the x-axis, never to the y-axis. So the reference angle goes from the x-axis and connects there. And I know that the sine value is -1 over 3. So I know that, let me just rewrite that real quick. Sine of alpha is equal to -1 over 3. So I know that the -1 has to be the opposite, or y value, and the 3 has to be the hypotenuse, or the r value. So -1 and 3 will have to go in those 2 positions. Now, it's possible that the negative might have to go with the other coordinate. If you were using a tangent or something like that, you have to figure out, based on this quadrant, which of these values should be positive, which should be negative. In this quadrant, we should actually have both a -x and a -y, and then we know that r is always positive. So this should come out as negative for the sine value when I have that ratio. Let's go ahead and find our missing side. I'm going to call it x because it is the x value there. So x squared plus -1 squared equals 3 squared. X squared equals, I should do first x squared plus 1 equals 9, then x squared equals 8. So x equals plus or minus the square root of 8. This time, based on the fact that I know I'm in quadrant 3, we are going to select the negative version of this radical. The x-axis is negative on this side, so I know that I need the negative square root of 8. We are going to simplify that to negative square root of 4 times square root of 2, and that gives us negative 2 square root of 2. We do want our radicals to be reduced. So the x-coordinate is negative 2 square root of 2. Okay, so we know the sine value. We need the cosine value. This is my angle alpha. So the cosine of alpha will be the angle that is adjacent. That's going to be the negative 2 square root of 2. That's the x-coordinate. Over the hypotenuse, which is 3. Then I need the tangent of alpha, so that's y over x, or opposite over adjacent. So y over x is negative 1 over negative 2 square root of 2. Those two negatives are going to cancel, so I can write it as 1 over 2 square root of 2. That could be rationalized. I'm not going to need to do it because it's not a special angle, so we'll leave that alone right here. We'll continue on, and those are the primary three. So let's go for the cosecant of alpha. That will be, flip this to 3 over negative 1, or negative 3. The secant of alpha, flip this to, I'm going to go ahead and write the negative still on the top. So negative 3 over 2 square root of 2. Again, it could be rationalized if needed. It's not needed on paper. And then let's flip this one. I'm going to flip it from the positive version since the two negatives are going to cancel again. So it's going to be 2 square root of 2 over 1, or just 2 square root of 2. Okay. All right. The middle of the page is actually kind of important here, so I'm going to highlight this. We've got some special cases where the terminal side of an angle is on an axis. So in this case, my angle is 90 degrees because I have my axis right there as the other side of the angle. So I actually can't close the triangle. There is no closure because the fastest way to connect to the x-axis is straight back down. So the triangle itself is actually, I shouldn't have highlighted the x-axis right here. It's got no height. The triangle is actually just this line. That is the whole triangle. So it's been collapsed. So the x-coordinate of this triangle is 0 and the height is 1. I can also have a triangle on the negative x-axis. Again, that is the entirety of the triangle. When you draw it to the x-axis, it's got 0 for its height, negative 1 for its x-coordinate. Your triangle can collapse back down onto the negative y-axis, or it can collapse back down the positive x-axis. In these cases, if you wanted to find the sine value, for example, in these, the x value is 0, the y value is 1, and the r value is also 1 because 0 squared plus 1 squared is still equal to just 1. So the r value is 1. Pythagorean theorem still applies. Okay. So if I was able to find the sine of 90 degrees right here, it's equal to y over r. So that's 1 over 1, which is 1. And if I wanted to find the cosine of 90 degrees, it's equal to x over r. So that's 0 over 1, which is 0. So I can find the sine and cosine of the 90, a 180, a 270, or a 360. We're going to find the rest of those down below when we make our chart right here that's going to expand our special diagram that we'd already done for the 30, 45, and 60. We're going to expand this to also include special angles for 0, 90, 180, 270, and 360. All right. So let's first consider if the angle is 0. If the angle is 0, that's going to be the same case as if the angle is 360. If you start on the positive x-axis and don't move at all, you stay in the positive x-axis. Or if you start on the positive x-axis and rotate a full circle, you land back on the positive x-axis. So the 0 angle and the 360-degree angle are going to have identical trig function measures. As such, the sine of 0, remember here that the x coordinate is 1, the y coordinate is 0, and the r value is 1. So sine being y over r, 0 over 1 is going to be 0. So the sine of both 0 and 360 is going to be 0. The cosine of 0 is x over r, so 1 over 1, which is 1 for both of those. Then the tangent. The tangent is supposed to be y over x. So the tangent of 360 degrees is 0 over 1. So that is 0. So that's going to be 0. And now we get into the cosecant. For the cosecant, I would need to take the r value, 1, divided by the y value, which is 0. So 0 divided by 1 is 0, but 1 divided by 0 is undefined. So I'm just going to abbreviate this right here. Undefined, undef, just for short for undefined. I can't fit the whole word in the box. So these are undefined. I'm not able to divide by 0. So if my sine value is 0, its reciprocal, 1 over 0 is undefined. If the cosine value is 1, the reciprocal, 1 over 1, is still 1. And the cotangent, 1 over 0, is going to be another undefined. All right, so those are our 0 and 360. Let's go ahead and finish the new ones, the 90, the 180, and the 270, before coming back and doing the ones that we previously knew for the 30, 45, and 60, since those won't change from what we previously learned. So 90. This is my diagram for 90. We already said that the sine of 90 is going to be 1 over 1, which is 1. And the cosine of 90 is going to be 0 over 1, which is 0. The tangent of 90 is going to be y over x. So that's 1 over 0. 1 over 0 is undefined. So the tangent is undefined. The cosecant is 1 over the sine. So 1 over 1, which is 1. And the secant is 1 over 0, which is undefined. And then the cotangent, 1 over undefined, I can't do. But remember that cotangent, instead of it being y over x, it's going to be x over y. So 0 over 1 is going to be 0. So we do have some pairings right here. For cosine and secant, 0 and undefined is a pairing. If cosine is 0, then secant's undefined. Same for tangent and cotangent. Tangent is undefined and cotangent is 0. Let's look at our 180. For 180, the x coordinate is -1, the y coordinate is 0, and the r is 1. So the sine, y over r, is going to be 0. The cosine, x over r, -1 over 1, is going to be -1. The tangent, y over x, 0 over -1, that's 0. The cosecant, 1 over 0, that's undefined. The secant, 1 divided by -1, that's still -1. And then the cotangent, 1 divided by 0, that's undefined. Okay, now we have the 270. In 270, the x-coordinate is 0, the y-coordinate is -1, and the r value is 1. So the sign is going to be -1/1 for y over r. That's -1. The cosine, 0 over 1. That's 0. The tangent, y over x, that's -1 over 0. That's undefined. The cosecant, 1 over -1 is -1. The secant, 1 over 0 is undefined. And the cotangent, instead of -1 over 0, we have 0 over -1, so that's going to be 0. Similar argument to 90 degrees. Okay, so before we get into, again, the 30, 45, 90, which we already saw previously, let's look for some patterns right here with our terminal side on an axis. We notice that the answer is either 0, 1, -1, or undefined for all of these because our ratios are built out of the numbers 0, 1, and possibly a -1. Okay, so there are some nice patterns with these. I notice as well that, let's see, the 0, 360, those were the same. And the 180, it's not the same, but it's pretty darn similar. The only difference is that the x-coordinate, instead of being a +1, the x-coordinate is a -1 for the 180. So when I have 0, I have 0. When I have 1, I have -1, and so on. So there's a lot of similarity between our 0 and our 180, as well as the 360. And then I also noticed that between the 90 and the 270, again, that similar relationship because it's 0, 1 versus 0, -1. So 1 turns to -1, 0 stays 0, and so on. So if I do know the 0 and the 90, perhaps I can also quickly figure out the other two, the 180, the 270, and of course the 360. So if I know those two, I do know the rest. Just consider the sign positive or negative on each of the values. All right, so we're going to go back and fill in the values from the 30, 45, and 60. So if you have your notes from a previous section, you can look back at those. So our sine of 30, if you recall, that was 1/2. And that matched up with the cosine of 60. So we'll fill in the cosine of 60 here as 1/2 as well. The cosine of 30, that was the square root of 3 over 2. And that matched up with the sine of 60 as the square root of 3 over 2. The tangent of 30, that was square root of 3 over 3. And that matched up with the cotangent of 60. So this one's also square root of 3 over 3. While we're doing tangent and cotangent, let's finish the cotangent for 30. That one is square root of 3. Pairs back up with the tangent for 60 as square root of 3. Then the cosecant of 30 is going to be the reciprocal of 1/2, so that's 2. Matches up with the secant of 60, that's 2. And then the reciprocal of square root of 3 over 2 is going to be 2 square root of 3 over 3. So that's the secant of 30, and the cosecant of 60 is also 2 square root of 3 over 3. When trying to remember between the 30 and the 60, let me just draw myself a quick triangle that has a 30-degree angle and a 60-degree angle. Okay, so if this is the 30 and this is the 60, I know that my x and y coordinates are either 1/2 or square root of 3 over 2. So in the 30-degree angle, the x coordinate is longer and the y coordinate is shorter. I'm going to have to write this underneath so I don't have space to write right here. So that means that this would have to be of the order square root of 3 over 2 comma 1/2, because 30 degrees is longer. It has the larger x as compared to the 60 degrees, right? So this is going to be the ordered pair on the 30-degree angle. The ordered pair on the 60-degree angle, that's going to have to be 1/2 comma square root of 3 over 2. So 60 degrees is taller. So it's going to have the larger y. See what I mean? By the larger y, the y value is the square root of 3 over 2 on the 60 degrees. And the x value is the square root of 3 over 2 on the 30 degrees. Now, if I use my definitions, in both of these cases, the r value is 1 for these ordered pairs right here. If I look at y over x, 1/2 over 1 is 1/2. Sorry, it was y over r for sine, y over r. Then this is x over r. And then this is actually their quotient, y over x. Okay, y value, larger for the higher angle. Sharing this as a way of remembering, if you know that those are the two possibilities, how do you fill in this chart if you needed to know these without being able to refer back to it? If you know for a 30 and a 60, your possibilities for coordinates are 1/2 and root 3 over 2. You can figure out which one's which, thinking about which triangle is taller and which triangle is longer. Okay, this has to be the shorter y coordinates. The sine value is 1/2 of the 30. This has to be taller, so the y coordinates root 3 over 2 for the 60. Trying to explain how I remember this. Hopefully that helps you a little bit. All right, let's fill in our 45 here. So our 45, we know x and y are both root 2 over 2. So sine and cosine are both root 2 over 2. And tangent is going to be 1. This makes the cosecant square root of 2, and the secant is also square root of 2, and then 1 over 1 is 1. So we filled in our 45 there as well. Okay. Another thought, let me see if it pops up on the next page. Nope, it doesn't. So I just want to say it now. Another thought I have about this is that the sine and cosine function values are always defined. I never had undefined in those two. So I'm going to make a quick note of that. It is going to come back up when we talk about domains of these functions later on. But sine and cosine are always defined. And then for the others, they always have two angles that are not defined. So for the ones that land on the axes. Okay, so at 0, 2 undefined, at 90, 2 undefined, at 180, 2 undefined, 270, and 360. So we'll just mention for the others, they're just not always defined. Right? So tan, cosecant, secant, and cotangent are not always defined. Right. Lots of things to observe and patterns to see in our chart here. Okay, so let's continue and look at example 5. Build a reference triangle and use it to find the sine, cosine, and tangent values for the following. All right, so 225 degrees. So let me start with a pair of xy axes. And I want to figure out how big this angle is. It's positive, so I know that I would have 90 degrees, 180 degrees, 270 degrees and then back to 0 or 360. 225 is between 180 and 270, so I'm going to draw it here. So this is going to be the angle 225 degrees. Now, I also want to know if I can figure out how far past 180 is that. What is the reference angle? So let's find out. So 225 minus 180. I only would want to do this if the reference angle is one of my perfect angles, if it's a 30, a 45, or a 60. This ends in 5 though, so I'm hoping that it might be. So let's clear this. 225 minus 180 is 45. So that means that inside this triangle right here, I have a reference angle of 45 degrees inside. So I can use what I know about a 45-degree angle to figure out the sine, cosine, and tangent values. Okay. So I know that, let me just make a quick note down here. I know that the sine of 45 degrees is root 2 over 2. The cosine of 45 degrees is another root 2 over 2. And the tangent of 45 degrees is 1. Those aren't the answers I'm looking for, but they're going to help me get them. What I'm looking for is the sine of 225 degrees. So, because I am in quadrant 3, I know that the x-coordinate is negative and the y-coordinate is negative. So that means that the sine is going to be negative. So it's going to be a negative root 2 over 2. Because I know that the y-coordinate is going to be negative. That's going to be a negative root 2 over 2. The cosine of 225 degrees. The x-coordinate is also negative in this quadrant as well. So it's also going to be negative square root of 2 over 2. Right, we have negative, comma, negative. That was supposed to just be two negatives in some parentheses. Negative, comma, negative for being in quadrant 3 there. And then our tangent, that's going to be negative divided by negative, which comes out positive. So that's still going to be equal to positive 1. Tangent is positive in quadrant 3. So these are the 3 values that we're looking for. And we use the reference angle to find the value, and we use the quadrant to find the sign, negative or positive. Okay. Continuing, let's look at the next one, negative 120. So I'm going to go backwards. This would be a negative 90. This would be a negative 180. So this is the angle negative 120. The reference angle to that would be the angle that went up to the x-axis, so it would be this angle here. So I need to figure out how far shy of 180 I am. So I'm going to take that negative 120, and I'm going to find the difference between that and 180. So I'm going to add 180 to it, and that will give me a measure of 60. So it's 60 degrees inside this triangle. So the reference angle here is 60 degrees. Okay. So I know that the sine of 60 degrees, remember that's the taller angle, so it's got the bigger value, root 3 over 2. The cosine of 60 degrees, that's got to be the smaller one, so it's 1/2. And the tangent of 60 degrees, that would be y divided by x. So if you divide these, square root of 3 over 2 divided by 1/2 is times 1/2, so the 2's cancel. That's going to be square root of 3. You can always look back at your chart, but you can also find them just by dividing those two values. And so the values that I actually want will be these with positive and negative sign adjustments. So the sine of negative 120 degrees, since we are in quadrant 3 again, needs to be negative. So negative square root of 3 over 2. The sine of negative 120 degrees. Okay, again, remember that for this point, the x-coordinate and y-coordinate are both negative. So it's going to be negative 1/2. And tangent of negative 120 degrees will be 2 negatives divide into a positive, so positive square root of 3. So it turned out that both of these examples were in quadrant 3, so they similarly had 2 negative coordinates. Very possible that if you were in quadrant 2 or quadrant 4, only one of the sine and cosine would be, this was supposed to say cosine, apologies. There we go. Sine, cosine, I did the right value for cosine over here, just wrote the function wrong. Busy talking. Okay. So if you're in quadrant 2, for example, the sine would have been positive while the cosine was negative, and the tangent would be negative as well. So whatever quadrant you are is going to affect the sign, the positive or negative sign. Okay. Interesting point down here. Very interesting point. Note that using the inverse trig functions only ever yields a reference angle, and it might not yield the actual angle that you're looking for. So that's a really important point right here. So inverse trig functions will only ever yield the reference angle. So that's going to come into example 6 right here. We may need to find an angle whose edge is coterminal with a given angle in order to figure out the answer to a question. Here, I know that the tangent of some angle theta is 0.2460, and this angle needs to be in quadrant 3. All right, so what I want to do first is find theta by taking the arc tangent of 0.2460. You make sure that I'm in degrees, which I don't think I am. Oops, degrees. There we go. And inverse tangent or arc tangent of 0.2460. So this angle is in quadrant 3. The angle that I got from doing arctangent is the reference angle. So this is 13.8. Now that's not the actual answer that I need to get here, because the actual answer needs to be measured from the positive x-axis over to this terminal edge. So 13.8 degrees is actually here, and it's not the correct answer because that angle is in quadrant 1, not quadrant 3. In order to find the angle that I do actually need, I need to measure it as 180 past 180 degrees, the negative x-axis, by a measure of 13.8. So if we take 180 plus 13.8, theta would be equal to, outside the parentheses, 193.8 degrees. And that's our actual answer. The measure of 13.8 is incorrect as an answer because it's not in the correct quadrant. So I'm going to make a quick note of it here, but that's not finished. To finish it, I need to put it in the correct quadrant. Now, I do want to compare real quick. If I do the tangent of 13.8, it does come out as 0.246 once you get this rounded correctly or rounded to a certain number of places, especially if you were able to keep a few more places after that 8.233. You're going to see it comes out really close to, there we go. I get enough places on there. The rounding pops into the 0.246. Okay. Now, the answer to my angle, that is my actual answer, the 193, is the same thing. This is an angle that's in quadrant 1. That's not the angle I was looking for. I was looking for an angle in quadrant 3. The only way for me to know that I was looking for an angle in quadrant 3 is to be told that I was looking for an angle in quadrant 3. Once I know that, I can appropriately add the 180 or subtract from 360, just depending if I was in quadrant 4, quadrant 2, or quadrant 3, to find the angle I was looking for. Let's give this another try. Okay, I've got an angle here where I know it's supposed to be in quadrant 4. And I know the angle's sine value is negative 0.4313. So I'm going to have to do the arc sine of negative 0.4313. And what that's going to give me is this little bitty angle in the reference triangle. Then I'm going to have to change that for myself. Okay, so the arc sine of negative 0.4313 comes out as negative 25.6 degrees. Hopefully you were expecting that negative because inside the triangle, that angle is in reverse orientation, so a negative angle is appropriate there. But we want to find the positive rotation of this angle, and we're going to add 360 to it to find the amount by which we are shy of 360. So this came out as negative 25.6. For our angle, we're going to take 360 degrees minus the 25.6, or negative 25.6 plus 360. So our angle theta in quadrant 4 has a measure of 334.4 degrees. Can check it. The sine of 334.4 should come out to the negative 0.4313. I don't have exactly that because I did round off a bunch of decimal places and apparently typed in a 0.4 instead of a 0.6. Wait, no, I'm good. Let me keep a few more decimal places right here and adjust just for fun. Copy. If I kept more places, it does round to 334.4. If I keep more decimal places, that's where you can see, yes, it does come out to the negative 0.4313 by keeping a few more places. So that's just for checking. We don't need to keep the places on the paper, but for checking, it didn't look like it was that close until I kept more places. Okay. Coming up on our last page here, let me get rid of decimals. We now need to find an angle so that the cosecant of that angle is negative 1.064, and that angle is in between 630 and 720 degrees. So let's think about how big that angle would have to be. We've got 0, 90, 180, 270, 360. So we know we've already spun around once. Then let's just keep adding. If we spin around twice, 360 plus 360, that was supposed to be at 360, would be 720. So this would be 720 right here if you spin around twice. This right here is 270 on the first rotation, 90, 180, 270. So if you spin around to 270 twice, so 360 plus 270, that's the 630. So this angle needs to be in between 630 and 720. So it's got to be somewhere in quadrant 4, where the measure of the angle is between the negative x-axis, or the negative y-axis here, I meant to say negative y-axis and the positive x-axis. So what this tells me is that I need to be in quadrant 4 with 2 rotations. Right. I had to interpret that to mean quadrant 4 with 2 rotations. So let's draw our angle in that quadrant. Drop up a reference line to get to the closest version of the x-axis. And I know that the cosecant of theta is negative 1.064. So I know one version of theta is going to be the arc cosecant of negative 1.064. I got to make sure I'm in degrees again. I think I am. Yes, I am. Arc cosecant of, move decimals a little bit, negative 1.064 gives me an angle of about negative 70.03. Okay. So typically I keep one place, but just because those decimal places, we'll just keep an extra one, just because it's a little bitty number there. That is the angle that is measured as backwards. So to get the angle that's measured forwards, I'm going to take negative 70.03 plus 1 rotation of 360. So 1 rotation would be 289.97 degrees. Okay, so this would be the clockwise. And this would be 1 positive rotation. And we need 2 rotations, so we're going to add in another 360. So this is now 649.97 degrees. And that is going to be my answer because it is in between 360 and 720, and that's what was needed. So it's that 2 positive rotations, had to add 360 twice to get it to be an angle of the correct size. All right. Okay. Last example now, number 8. Hopping in your Cessna, you fly at a speed of 110 kilometers for 3.2 hours at a bearing, we need to remember what bearing means from our last section, of 319 degrees from Jackson. How far north of Jackson's latitude are you at that point? Okay. First, I need to remember what bearing means. Bearing is always measured clockwise from north. It's not a standard angle, which is measured counterclockwise from the x-axis. It's clockwise from north. So north, south, east, west. 90, 180, 270. Right? If I go 90, 180, 270 clockwise from north, that would put 319 over here. Okay. So my airplane has ended up there. And I flew at a speed of 110 kilometers per hour for 3.2 hours. So I know that I've gone a distance of 110 times 3.2. I've gone a distance of 352 kilometers, right? 110 kilometers per hour times 3.2 hours is 352 kilometers. What I want to know is how far north of Jackson's latitude are you? So we're looking for the vertical distance right here. So if I complete this triangle, what I'm looking is how far in the northern direction did you go? Okay. All right. So what I need to figure out is from this angle of 319, what is the reference angle? What is the angle that's actually inside this triangle? So I know that I've got a 90 in this quadrant, a 90 in this quadrant, and a 90 in this quadrant, or a total of 270 around here. So I'm going to have to take that 319 minus 90, 90, 90, or minus 270. That's 3 times 90, right? To figure out this angle, to figure out the amount left over that's in the triangle. So 319 minus 270 is a measure of 49 degrees. So the reference angle for this is 49 degrees. In this case, I cannot use the sine, cosine, whatever of 319 itself because that's not a traditional measure. The sine measures always measure from the x-axis itself. Okay. And this is measuring from the x-axis. I also could use, I can use a theta, which has 49 degrees as its reference angle. Reference. Missed the R in there. Reference angle. Or I could use the true angle here, which is 49 degrees shy of 180. We'll talk about the differences between those in a second here. So 180 minus 49 is 131, and that is the actual angle. The only difference between using the reference angle and the actual angle is for the reference angle, both sine and cosine are going to be positive. And for the actual angle, the cosine value is going to be negative and the sine value is going to be positive. It's not going to turn out to matter for this particular question because we're looking for the y coordinate, which is going to be positive in both of those. So it's going to be okay if I set it up in terms of either of those, as long as I know the sign of those is both positive. All right, so let's go ahead. We're looking for this side. I'm going to call it y, just because x would be the x coordinate, y would be the y coordinate. And we're going to say that we know that the sine of, doesn't matter which of these, let me go ahead and use the actual angle. So the sine of 131 degrees is going to be equal to y over 352 kilometers. Multiply both sides by the 352. Gives us that whatever 352 times the sine of 131 degrees is going to equal y. Okay. Again, I'm just going to make sure I haven't cleared this. I'm still in degree mode, so that's good. And we're going to multiply 352 times the sine of 131 degrees. This gives us 265.7 kilometers for y. Real quick before we continue, I wanted just to show that the reference angle, which would have that 49 degree in it, is going to give me the exact same value. So if you use the reference angle, that's exactly okay. Because as we said earlier, we knew that the y coordinate was going to be positive. in both the reference angle, which would have been a quadrant 1 angle, 49 degrees over here, would have positive, positive, versus this one, negative, positive. If I was looking for the x-coordinate and I use the cosine, that's when I would need to differentiate between the two angles because the sign, the positive or negative sign of the cosine value is different. But for the sine function, it was positive in both of these two coordinates. So it's actually okay to have used either of those, and it doesn't actually matter which one you did. But I wanted to talk about that distinction to make sure we were considering the sign of the sine function, the positive or negative sign of the sine function. All right, that's the end of this section.